Good day, good people. In today's lesson, we are going to be studying A-level further pure mathematics. We are looking at roots of polynomials. Before we get into the lesson, I want to give a disclaimer. The disclaimer goes, A-level further pure mathematics, as the name of the subject suggests, we are going to be furthering pure mathematics. So we are going to be assuming a lot of things. So what you learn in pure mathematics, that is A-level, is going to be largely treated as assumed knowledge as we study further pure mathematics. But I'm going to be digressing a lot. I'm going to be revising and recalling a lot of concepts which you learn in pure mathematics so that you can understand further pure mathematics a lot more. Firstly, we are going to start with defining terms. Our subheading, of course, is going to be roots of polynomials. So the color coding of this lesson, we are going to be writing down what we suggest you write down as notes in the color white. Then all other colors are going to be used for illustrations. Before we get much into our subject matter, which is studying the roots of polynomials, we need to define terms. And the first term we want to define is the term polynomial. So we want to give a definition of the term polynomial. So what are polynomials? There are many ways of defining polynomials, but one of the easiest and easily to understand ways of defining polynomials is stating that a polynomial is an algebraic expression. It can also be an equation of the order n. So we can define a polynomial as an algebraic expression or an algebraic equation of the order n. We are going to define what an order is, but before we do that, let us give an example of a polynomial. So an example of a polynomial, it can be 4x cubed plus x squared minus 4x minus 1. So this is an example of a polynomial. Of course, this is an algebraic expression. We can easily make this an equation by equating it to any number or any term, but in most cases, we equate it to 0. That is if we want to solve it by either factorization or other methods. So that is an example of a polynomial. What do we learn from that example? Firstly, we have to recognize that all the terms of that polynomial is an example, but generally all the terms of a polynomial are positive integer powers of a variable. What do we mean by this statement? An example would be taking from this polynomial x squared, and we can also have 4x cubed. So what we are talking about by this statement, all the terms of a polynomial, so this is a general statement, all the terms of a polynomial are positive integer powers. So this is a very important part of what we are talking about. They should be positive integer powers. Let us look at the powers we have. In this polynomial, we have the power 3, we have the power 2, then here we also have the power 1. We can do so, or we can actually add x to the power 0 here, because any number, any term raised to the power 0 gives us 1. So if we say minus 1 times x to the power 0, that is the same as saying minus 1 times 1, which gives us minus 1. So by multiplying this constant with x to the power 0, we do not change the value of that constant. So these are the powers we have: 3, 2, 1, and 0. Of course, here we said 1 because if it is just a variable, we can raise it to the 1. That does not change the value of that variable. So that is the reason why we said minus 4x to the power 1. All these powers, if it is a polynomial, they should be positive integer powers. We cannot have negative powers. We can also not have fractional powers. So to further elaborate on this point, what we are actually meaning is there are no square roots and we have square roots from fractional powers or reciprocals. And we get reciprocals from where? From negative powers. The characteristic of a polynomial, when we look at the powers within or contained in that polynomial, those powers should be positive integers. They should not be fractional. They should not be reciprocal. So if we are to give an example, let us say we had a situation like 4x squared plus 3, the square root of x, plus 4 over x. This is not by definition a polynomial. Why isn't it a polynomial? Because it has this part. This part can be expressed as x to the power half. So it has a fractional power. Secondly, it has a reciprocal because this part can be written as 4x to the power minus 1. So that is a key characteristic of what a polynomial is: positive integer powers. But we wanted to define the term order. So let us now look at what this term refers to. So when we talk about an order, this is the largest power of a variable in a polynomial. So when we have a polynomial, an algebraic expression or equation, the largest power of the variable in that polynomial is what we call the order. So an example would be, for this polynomial which we are using, 4x cubed plus x squared minus 4x to the 1 minus, let us just say minus 4x here. Let us write it as it was originally written, then minus 1. For this polynomial, the order is 3. Why are we saying the order is 3? Because the largest power of the variable here is 3. So since the order is 3, this means therefore the polynomial is cubic. That is what it means. So the order of a polynomial gives us the nature of that polynomial, or the family of equations, the family of expressions where that polynomial belongs to. We can double down on this. Of course, this is going to be more like a recall. You are supposed to have learned this in your ordinary level mathematics, also in your A-level pure mathematics. So what do we want to recall? Let us put down a table here. We have an order. Then we have, maybe we can call this nature, like that. And let us have an example here. so that we can better understand what we are talking about. Let us say we have the order 1. And an example of an expression where the order is 1 would be something like x plus 3. What we have here is called a linear polynomial. Linear in the sense the highest power of the variable is 1, as we have there. So that is where we get linear equations. Let us move on. Say we have the order 2. An example here would be x squared plus maybe 3x plus 4. A more general example is basically ax squared plus bx plus c. A general example here would be mx plus c. And I'm taking this mx plus c from the general expression of the equation of a line. Remember, the equation of a line is y is equals to mx plus c. That's why I chose mx plus c there. So m and c, of course, they are just real numbers in most cases. What is this called? This is called quadratic. So you see, the order tells us the nature of the polynomial we are dealing with. If it is a linear polynomial, the order is going to be 1. If it is a quadratic polynomial, the order is going to be 2. How about we have an order of 3? And an example here would be x cubed plus x squared, maybe plus 4. Sometimes we have situations where we do not have every power represented. Like in this case, we don't have x to the power 1. What's important is to take note that the largest power inside this polynomial is a 3, which makes the order 3. And the nature of this, it is called cubic, as was in our example. That is the reason why we concluded the polynomial is cubic. And a more general expression of a cubic polynomial is ax cubed plus bx squared plus cx plus d. These general expressions are going to be important, so please take note of how we write them. Of course, this was common in your O-level mathematics. Even in your A-level pure mathematics, you came across this, but this might not be as common. So this is the cubic general expression, or general expression of a cubic polynomial. Now, having done so, let us now get to what we really want to learn today. So it is important when we are studying polynomials to be able to draw up, or rather to have a basic understanding of their graphical representation. What do I mean? When we are learning about polynomials, we should also know their associate graphs. So an example here would actually be when we are looking at a linear polynomial, we know that the graph is going to be like this. So it can be like this. It can be like this. There are many expressions of it, dependent, of course, on the gradient of that particular linear polynomial. But these are just examples. Then when we go over to the quadratic, the associate graph is going to be more like this. Or it can be like this, in a case where we have a maximum turning point. If we go to a cubic, and we usually have cubic polynomials or cubic graphs when it comes to drawing the graphs of trigonometrical functions. Now we are talking about something like this, or it can be something like this. That's cubic. But what we have to learn here is a certain general statement. So let us put down the general statement, then we can explain what we want to learn. So generally, and the term generally is very important, a polynomial equation of order n has n roots. Generally speaking, a polynomial equation of order n has n roots. The general statement is a polynomial equation of order n has n roots, generally. So the number of roots for this quadratic polynomial is 2, because the quadratic polynomial is of order 2. The order here is 2. What about for a cubic? Generally speaking, we are going to have 3 roots, because the order of a cubic polynomial is 3. Same is going to apply for the quartile. Same also is going to apply for the linear situation, where the order is 1. But if it is a general statement, it means it does not always apply. So let us expand this general statement. How are we going to do so? Maybe let me write, but we may have repeated roots and complex roots. Repeated roots for a quadratic polynomial are the easier to understand, because this occurs when the discriminant b squared minus 4ac, when the discriminant is equal to 0, then we have a situation where we have a repeated root like that. So if you don't remember this, you obviously have to revise the topic quadratics from your A-level pure mathematics. This is feathering, remember. Okay, what about complex roots? When we speak about complex roots, you have to understand complex numbers, which actually have a general statement x plus y I, where x is called a real part, it's a real number, and yi is now called an imaginary number. And we of course know that I is equal to the square root of minus 1. That is actually the founding principle of complex numbers. We are going to take I as the square root of minus 1. Okay, so sometimes we have a situation where our roots are actually complex roots. And sometimes we have situations where we have repeated roots. But generally speaking, a polynomial equation of order n should have n roots. Now what we want to do is, we want to exemplify what we have learned with 2 polynomials. So polynomial number 1 is going to be the function of x is equal to 4x cubed plus x squared minus 4x minus 1. And our second polynomial, the function of x is equal to 4x cubed plus x squared plus 4x plus 1. So if you look at these 2 polynomials, we have just twitched a little. We changed the sign of minus 4x to plus 4x, did the same for the sign of minus 1 to plus 1. So to the eye, they really seem similar, just a small twitch. But when we try to graph those 2 polynomials, you are going to see how different they are. So now I want to introduce you to a certain software Of course, in either Cambridge, ZIMSEC, Metric, or high school examining boards, I do not think you are going to be allowed to be using this software, but I'm going to introduce it to you so that it becomes more like extra help. You can use it for practice or when you want to visualize the associate graph of a certain polynomial. The name of what we want to talk about now, the software, is Desmos. So we are going to be taking those two polynomials to this software Desmos. We want to graph them so that we can see how the graphs are going to appear. So to access Desmos, I'm going to be using Microsoft Edge, but of course you can use Chrome, Opera, or what have you. Then I'm going to type in Desmos. Then of course I select this part. So this is Desmos. It's actually called a graphing calculator. We press it on. Once we have accessed Desmos, we should then put in the polynomial. So the polynomial is going to be 4x cubed plus x squared, then minus 4x, then minus 1. So this is what we have. Look at this graph. How many roots do we have? We have 1, 2, and then 3. Remember, we defined a root as the solution to a polynomial, or rather, a root is the point our curve is going to be crossing the x-axis, the point where y is 0. So this is a root because y is 0 and x is minus 1. So minus 1 is a root. Here we have minus 0.25 as a root. Here we have 1 as a root. So this has 3 roots because it is cubic. Remember, the order is 3. So when we come back here, we look at situation number 1. We are going to see that the graph is going to roughly be like this. So we have the roots. We have minus 1 as a root, minus 0.25, and 1. So the graph is like this. The emphasis here is not on how I've drawn it. The emphasis is on the 3 roots, supporting our thesis that generally speaking, the roots of a polynomial of order n are going to be n. Okay, let us now look at situation number 2. For situation number 2, our function is simply the function of x is equal to 4x cubed plus x squared. Then this part is a plus. It's plus 4x. And that part is also a plus. So this is what we have. Now look how far the graph has changed. And here the graph is actually only showing 1 root, which is minus 0.25. We only have 1 root there. Such that if we return here, for our case number 2, the graph is going to be like this. The only root we have is this part, minus 0.25, and this is our graph. So for a situation like this, we have 1 root, but this 1 root, we actually call it a real root. So we have 1 real root and 2 complex roots. So since a complex number is an imaginary part, the reason why we cannot pinpoint where these complex roots are it is because they are imaginary. For the first situation, we had 3 real roots. So the last lesson I want to teach you here is when you talk about roots, it's important to specify that they are either real or they are complex. And of course, sometimes real roots are going to be repeated. That is important. This is the end of our first lesson on the roots of polynomials, further pure mathematics. If you enjoyed the lesson, may you please consider subscribing, liking, commenting, and also sharing. If you want to be part of our school, if you want to learn further pure mathematics, maybe you want to learn advanced level pure mathematics, you might want to learn ordinary level mathematics or ordinary additional mathematics. Whatever math you want to learn, you can join us in our school, the Math Hub, Mathematics and Start on Ascending. To do so, you have to WhatsApp us on +263 71 521 3310. +263 is the Zimbabwean code. So if you are in Zimbabwe, it will simply be 071 521 3310. Thank you and have a nice day.